Hello and welcome to Module 2 of the course on genomic selection. In this module we're going to talk about what is genomic selection. So let me start with just a description of genomic selection itself. Genomic selection is a form of marker-assisted selection. It was first proposed by Mewison in 2001. So we'd like to think of this as a new breeding tool, but you can see it's actually been around for 16 years. And what you do in genomic selection is you use phenotypic and genotypic data from past trials of lines to build a model, and that model is used to predict the value of individuals that have not been phenotyped. And what this does, is, in contrast to marker-assisted selection, it uses marker data from the entire genome to predict the values of individuals. These are called genomic estimating breeding values, or GEBVs. So let's contrast genomic selection versus marker-assisted selection for a few genes. Both actually do use marker data to predict the value of individuals. In marker-assisted selection, you estimate the effects of markers one at a time, and then you use the data from those markers to predict the value of individuals based on a few genes, key regions of the genome, but not the entire genome. And this is quite effective for a few genes that have large effects. Genomic selection. It estimates the value of individuals using marker data from the entire genome, not a selected few markers, but all markers are go into the model to predict the value of an individual. This can be very effective for traits controlled by many genes with small effects. Genomic selection can be combined with marker-assisted selection for genes with larger effects. These two approaches are not exclusive. And genomic selection is a little bit more of a breeding tool than a research tool. Marker-assisted selection, we map genes, we get QTLs, we publish papers. It's a bit of an academic exercise at first. Genomic selection truly is a breeding tool. It is useful in variety development to improve your efficiency and improve your probability of finding products that can go out to your growers. The principle of genomic selection is actually quite simple, while the statistics underlying it can be pretty dense at times. It's really based on the oldest observation in genetics, and that is that individuals that are highly related to one another tend to look alike. They tend to act alike. They tend to perform alike. All right, and so really you can use data from relatives to predict the value of individuals. And it's just shown here in this graph. Here we have a genetic relationship among 10 individuals based on markers. It's a principal component analysis, and you see that the 10 individuals have been pretty neatly put into two different groups. Now let's say we take those 10 individuals and we phenotype them. The upper group has an average phenotype of 100 units. The lower group has an average phenotype of 70 units. Now we have an 11th individual. We don't phenotype it, we just genotype it. Based on that genetic information, we find out that that new individual is highly related to those ones in that lower left box that have an average phenotype of 70. So now we need to predict its phenotype. And what do you think its phenotype, what would you predict its phenotype most likely would be? 70 or 100? It's not a trick question. Clearly, you predict that the value of this individual would probably be close to 70, because that's the value of its relatives that it's highly related to. So, genomic selection estimates the relationship based on markers that cover the entire genome. It uses this relationship to predict the value of unphenotyped individuals that have been genotyped. And you can actually use this relationship to enhance prediction of predicted value of individuals that have been only lightly phenotyped. For example, lines that enter your first stage of phenotyping in the field. They may be tested in one plot in one location, maybe one plot in two different locations. But your advanced lines are probably tested with multiple reps and multiple locations. There's a lot of data on them. You can determine for your lightly phenotyped lines what is the relationship to densely phenotyped lines, and use the information from those relatives to predict the value of those lines that have been only lightly phenotyped. And that can improve your predicted values of those lines. So the more related individuals are, the better the predictions are. And I'm just showing this by showing an example, a relationship matrix between 5 individuals, designated individuals A, B, C, D, and E. And all we're showing here is the relationship amongst these individuals. And the numbers in there simply show what proportion of the genes are in common between 2 individuals. Like individual A and B, 90% of their genes are in common between them. A and C, 80% of their genes are in common. A and E, only 10% of their genes are in common. So based on these kind of numbers in this matrix, we can determine which individuals are highly related to one another and which ones are distant relatives. Now, if I wanted to do predictions, data from individuals B and C would be fairly useful in predicting the value of A. Data from D is less useful predicting the value of A, and data from individual E is the least useful for predicting the value of A. So it's all based on how related individuals are. There's some details of this relationship matrix. I'm not going to go into them here. I think it's self-explanatory. Again, you can pause the presentation and look at those if you wish. So just having an overall matrix of genetic relationships, you can predict the value of unphenotyped individuals based on how related they are to phenotyped individuals. You can also use genomic selection to predict values of individuals based on data from individual markers. And I'll show you an example of that here. Let's say we have a particular marker, and I'm just showing it diagrammatically here as if it's scored on a gel. Individuals are small a, or they're heterozygotes, or they're large A. And let's just say we have a population, 8 of them are small a, 7 of them are large A, and they've all been phenotyped. And here's their phenotypic data there in this column headed by Y. And let's just plot that out. Okay, here are the phenotype of the 8 small a individuals plotted out. And the large A's, they're plotted out. Their phenotype of those 7 individuals are plotted there. So we have a nice graph showing our relationship of phenotypes on the y-axis with genotypes on the x-axis. Now we can change the scaling in the way we designate that x-axis, and let's make it numeric. Okay, now the scale is how many copies of large A do these individuals have? Large A obviously has 2, small a obviously has 0, and we can change the scaling a little bit more and have it so it's centered at 0. Small a individuals are scored as -1. Large A are scored as 1. And those are our values for X. And those are shown over here in this column. Now we have 2 columns of numbers, an X and a Y, and we can do a regression. We do that regression, and in this example, the slope is 3.1. What that means is every time I add a large A, I'm increasing the trait by 3.1 units. That is basically assigning a breeding value to that locus. And now we can use the relationship among individuals based on that locus to predict their value. If an individual had a value of large A, in other words, on the x-axis it was scored as a 1, well, we'd predict its phenotype would be similar to these. So again, it's really looking at relationships, but this time based on one marker in this model. Well, we do this in genomic selection using all the markers in the genome. So through genomic selection, we actually obtain the slope of these regressions for all markers. We do this simultaneously by treating them all as random effects. And what this does is constrains us so that all the variation explained by the markers is equal to the genetic variation in your population, and it cannot be greater. it will add up to the genetic variation in your population. Now, if you do a GWAS, you'll find that the variation modeled by the markers will be much greater than the genetic variation in your population. When you estimate these values one marker at a time, like you do in the GWAS, you're really getting upwardly biased estimates of their values. So genomic selection does it all simultaneously. Okay, and so let's say we have these 10 markers shown here. We have the slope for each one of them shown over here, and we can use those values, those 10 markers, to predict the value of individuals. Let's say here's individual A. Okay, marker 1, it had a value of -1. It was small a, it was the recessive, double recessive. And we take that value times the slope for that marker, and we come up with a value for that marker for that individual of 1.2. Here's another one. The slope of this one was 1.1. Individual A had a marker score of 1 for that marker number 5. Multiply those two values together, and you get the breeding value for that marker for individual A. Then all you do is you take all these values, add them up, and you get the predicted value for individual A. Individual B, do the same thing. We have its marker scores. We got the same values for the slope for each of those 10 markers. Do the multiplications, okay, get the products, add them up, and the breeding value, the genomic estimated breeding value, the GEBV of individual B would be 4.6. Notice individual A and B have nearly identical genotypes, and therefore they have nearly identical predicted values, because A and B are highly related to one another based on these 10 markers. Here's individual C, and it has exact opposite marker scores of individual A. And indeed, when we sum up the breeding value for each of the 10 loci, its breeding value for individual C is -5.2. The exact opposite of A, because its marker scores are the exact opposite of A. So this whole approach looks very different, for a different way of estimating genomic estimating breeding values than using a relationship matrix, but it gives identical results. Here we're looking at relationship of individuals based on individual markers versus the overall genome, and the results again come out to be identical. We will continue this discussion in the second part of this module 2.